for, I guess, the rest of it. So let's take a look what's going on. So here we are this week. There's makeup lab time if you're going to make up a lab. That's what you're doing today. So in other words, if you don't have any labs to make up, in other words, if you haven't missed any, then you're not required to show up tomorrow afternoon. If you did miss one, and you want to make it up, that's what you can show up. Also, if you just want to come and screw around, even if you don't have a lab to make up, you can certainly come on in and and do whatever it is you like to do. I'm going to be there regardless. So again, you're not required to come tomorrow afternoon unless you have a lab to make up, and even then, you can come or not come. It's completely up to you. Or you can come screw around, whatever you like to do. 100% up to you. But I will be there. Next week on the Monday, I'll probably just hang out. I'll come online, and if anybody has any questions, anything they want me to answer, that sort of thing, I'll hang out. And then, of course, I'm also thinking, the test. Well, next week there's no lab, so what I was going to do is I was going to put the test on the Tuesday, but I'm wondering, should I do the test on the Monday when we usually do our lecture? The only disadvantage to that, I suppose, is that you don't get a Q&A the day before the test, but you can certainly email me anytime before the test. So what I'll do is maybe I'll send an email out and ask you, what do you think? Do you want to do it on next Monday during your regularly scheduled online lecture time? Or do you want me to schedule it for the Tuesday? For me, it doesn't matter. It's 6.5 dozen of the other. But if I do it on the Monday, then I get your final marks in faster. That's pretty well the advantage. So right now I'm leaning towards doing it for the maybe the Tuesday, only because it gives me time to talk to people on Monday. But I guess majority rule. So I'll email everybody and see what you feel. It doesn't matter to me. It doesn't matter. Anyway, but regardless, your final test is going to be next week. It is going to be online. It's either going to be Monday or Tuesday. 100% to you. I know on the Tuesday, if somebody could answer me right now, on the next Tuesday, are you on campus before that lab time? Is there a class running on campus or a test on campus or not? You are on campus. Okay. So yeah, I wasn't sure if he was going to do it. So see, there it is again. Like if I do the test on Tuesday, I guess I can do it later. Or I can do it on Monday. Again, I don't answer me right now because I'll send an email out and I'll see what kind of responses I get back. As it stands now, I'll just leave things as is and I'll do it on the Tuesday. But there you go. So anyway, like I said, just to reiterate, we'll do the test overview. You are not required to show up tomorrow unless you have a lab to make up, and that's 100% up to you. I'm not waiting. I don't have a list of people who've missed labs. If you've missed a lab, come on over. You don't have to make the lab up. It's 100% up to you. Or if you want to just come and play with the equipment, then you can show up because I'm going to be there one way or the other. Okay. Okay, so just like last test, I'll record in a second. Just like last test, this test is, whatever you see on this overview is what's highly indicative of what's on the test. There's no more on the test. There might be a little less on the test, which is better be over prepared. And if you recall on my first test, it was pretty straightforward in terms of the topics that you had to go over. So you don't get retested on anything you've already been tested on. So it's test one and it's test two. Test one, all those topics are dealt with. So test two is going to be with anything that we've done after test one, as you'll see today. Okay. So again, this is already online. It's been online since the beginning. All I'm going to do today is maybe point some things out and give you some heads up in terms of what's important for the test. So let's do that. Oh, by the way, I might want to draw on this, and if I want to do that, I can't answer chat at the same time I'm doing the PowerPoint. So if you have questions, you can type them, but I won't be able to get to them until I'm finished going through the PowerPoint. Okay. And of course, I'll leave a Q&A, time for Q&A at the end. Right. So let's do it. Okay. All right. So this in and of itself is not important. You're not going to get a diagram on the test that says, "Hey, label these parts." But what is important is that when you're looking at the construction, you recognize that when we're talking about the field windings, they're in the stator. They surround the armature, and the armature consists, of course, the armature windings and the commutator. Right? That's pretty important in terms of not only the commutator, but what does the commutator do, and what are the brushes for, and things. And we're going to review that. So again, the field windings are the ones that are in the stator that surround the armature. The armature is a rotational part of the motor, and it consists of armature windings and the commutator. So again, we have windings, we have the commutator. If you had to answer what a commutator was, it essentially converts DC into AC, and it does that through the brushes, which we're looking at in a second. Because for any motor, it has to have an AC component, because there's no way for it to spin unless there's an AC component. But if it's a DC motor, you don't apply any AC, you apply DC, and then through the brushes, that DC is applied to the commutator. The commutator, as it spins, reverses the polarity periodically of that DC current, creating an AC voltage or AC current, which gives us an alternating magnetic field, and that interacts with the field windings, and you get rotation. So the commutator essentially is a mechanical rectifier. It rectifies the DC into AC mechanically. So the commutator obviously has those segments, and the brushes are set against the commutator so that they're 180 degrees apart from each other, because you need a positive and a negative side. The brushes generally are made of carbon, just like pencil lead. And that's pretty important because it has to be softer than the commutator, because otherwise it would damage the copper on the commutator. Brushes are always going to be in pairs, so you can certainly have more than 2 brushes, but you can't have like 3 brushes or 7 brushes. They have to be in pairs because you need a positive and a negative component. So 2, 4, 6, 8, 10, 12, you name it, you can have as many brushes as you need, depending on how much horsepower. But the models that we've been using and the motors that we've been using deal with just the 2 brushes. So again, the brushes are basically solid carbon, and they are used to apply the DC to the commutator, which then in turn mechanically changes that applied DC into AC, so that the armature has an AC magnetic field that interacts with the stator field windings. There's two basic types of DC motor. There's a third type that's the compound or the combination of the two. So the first type is the shunt winding. It could be any kind of switch. I have a drum switch because this is actually from another college when I taught there. But when you close that, you're obviously going to get the same voltage put across the shunt winding and the armature winding. This is good for the shunt winding is good for speed regulation, because the current through the shunt winding doesn't change as the load on the armature changes. So that means you get a pretty consistent magnetic field surrounding the armature, which helps to calm big swings in speed change. So that's why it has good speed regulation. When we're looking at a shunt winding, those 4 bumps are actually meaningful, because when we go to the series, it has 3, and that is not a mistake. That's actually how they're represented on schematics. What else should we know about the shunt winding? Well, we should know that of all the windings in a DC motor, you've actually got 3. You've got the shunt, you've got the series, and you've got the armature windings. The shunt winding has the highest resistance, and you of course saw that in your labs. When you did the resistance measurement, you found that the shunt winding was quite a bit higher than either the series or the armature. And that's because if it were low, then the total resistance would drop significantly, and you'd get too much current flowing into the motor. Right? So again, shunt is just another word for parallel. Shunt winding is connected in parallel. And with the armature, the shunt winding has a higher resistance than the armature or the series winding. And the shunt motor itself has good speed regulation because of the unchanging magnetic field around the shunt winding. When it comes to the series motor, the windings of the field, the series windings have very low resistance because they're meant to be placed in series with the armature. If you had a higher resistance on the series, then you get too much of a voltage drop across the winding, which means you would steal speed from the armature. And of course, if you remove speed or if you remove voltage from the armature, that means that your speed is going to drop. So you'd get a slower armature if there was too high. So if you were to put a shunt winding in series with the armature, then you'd get a significant voltage drop across the shunt winding, and the armature would spin extremely slow. If you were to put the series winding in parallel with the armature, you'd blow your fuses or you'd blow your overloads because there would be far too much current being fed into the motor. So the 3 bumps indicates that the series winding, the leads for the series winding are S1 and S2, just like with the shunt winding, I don't have it here, but it's F1 and F2. And of course, A1 and A2 are the armature. So what do we know about the series motor? We know that it is really good for torque because 100% of the current that gets delivered from supply eventually gets delivered to the armature, unlike the shunt where the current gets split between the shunt and the armature. That means because I have higher current, I have higher torque, because current and torque are directly related with each other. It does not have as good speed regulation as a shunt motor because the current through the series will fluctuate as the load on the armature fluctuates. So that magnetic flux is not going to be steady, and that does not provide good speed regulation. It doesn't mean you can't get good speed of a series motor. It just means that if there's changes in the speed of a series motor, they'll be a lot more abrupt. There won't be as much regulation as there is in the shunt. There's another aspect of a series motor that we've discussed, and that is it must be run with a load attached to the shaft of the motor. So if you start it without a load, or if while it's running, the load becomes disengaged from the motor on the shaft, then it goes into something called runaway. And I demonstrated that if it's two labs ago where we removed the load and we saw the speed climb and climb and climb, and we shut it off. And of course, the issue with runaway is it goes faster and faster and faster. But what do we know about speed and torque? Well, the faster it goes, generally the less current it's going to draw, though with a DC motor, it's a little bit different. So it's not really the current that damages the motor, it's the mechanical, the centrifugal forces in the motor that start to blow that thing apart. So shunt motor is good for speed regulation, not as good torque characteristics as the series motor. Series motor has superior torque characteristics, but not as good speed regulation. But the one thing we have to be aware of with series motor is that it must be run with a load, or the load cannot be disconnected while it's running, because it will go into runaway, which means the speed will just keep on going and going faster, which can result in mechanical damage to the motor, among other things, anything attached to it. So put them both together and you get a compound motor. And the compound motor compromises a little bit on the speed regulation but it gives you a little bit better torque than the shunt winding. Compromises a little bit on the torque, but gives you better speed regulation than the pure series motor. Compound motors are probably the most common because you can use them as compound, you can use them as pure shunt, and you can use them as pure series, just like we did in the lab, if you recall. That was actually constructed as a compound motor, but we were able to put it in a pure shunt or pure series configuration. So looking at all three, there's one thing we have to talk about, and that is, of course, direction. So when you're looking at the shunt motor, there's two ways to change the direction. You can change either the polarity of the shunt winding or the polarity of the armature. Same with the series motor. You can change either the polarity of the series winding or the armature. You can't do them both because it'll go the exact same direction. But when it comes to the compound motor, we can't do that because if it does that, then we'll have the current in opposite directions through these windings. So here, let me just go back to here because I forgot to record. I said I was going to record. Okay. So anyway, real quick. Commutator changes DC into AC. the brushes bring the external DC to the commutator, which creates AC within the armature. We have the shunt, the series, and the compound motor. Shunt's good for speed regulation, not as good for torque compared to the series motor. The series motor is good for torque, not as good speed regulation as compared to the shunt. The one thing about the series motor is that it will go into runaway if it is run without a load or if the load is removed while it's running. Okay. And of course, a compound motor is a combination of the two, where you compromise a little bit on speed regulation to get better torque, and you compromise a little bit on the torque to get better speed regulation. And the way to reverse this motor, the only way you can reverse the direction is to do swap A1 and A2, because the current through the shunt and the series must be going in the same direction. That's called cumulatively connected. That means that the magnetic fields are going to be the same polarity, so they'll add together. Whereas if you reverse just one of the windings, they become differentially connected, which means that you have opposite polarity in terms of the magnetic fields around the windings, and you'll end up with problems in the motor. Counter electromotive force. What should we know about counter electromotive force? Well, how much counter electromotive force is being generated by a motor at initial startup before it begins to spin? Well, that's zero, of course, because the only way for you to produce counter electromotive force in a motor is for your armature or your rotor in an AC motor, but your armature in a DC motor to start rotation. And what also do we know about the level of counter electromotive force? We know that the faster our armature spins, the more we generate in terms of counter electromotive force. And that's important because when we're looking at an FLA, in this case, the motor is rated at an 8 FLA. When we see an FLA rating on a motor's nameplate, we should just be aware that it is the mathematical difference between how much CEMF is being generated and how much current would flow into the motor if there were no CEMF, right? So, because if you have no counter electromotive force, which means this isn't spinning, but we've applied voltage, then it's drawing 38.3. But then once it gets up to rated speed, it's generating 30.3 amps through counter electromotive force. And if you subtract it 2, you end up with 8 amps. So it's important to know that the FLA rating, nameplate rating of a motor, is the mathematical difference between the amount of counter electromotive force that the motor would generate at rated RPM and the current that would flow into the motor if it wasn't generating any counter electromotive force. Right. So the faster we spin, the more counter electromotive force. That's why speed and current are inversely proportional. The faster we go, the less current flow we have into the motor, because as we go faster, we generate more counter electromotive force, which counters the current that's flowing into the motor, and therefore we get a drop in current. If I slow a motor down through overloading, say, the shaft, what happens? Well, if I slow it down, it's going to draw more current from supply, and that is what the purpose of overloads are for. Overloads are there to prevent overload of the motor. And how does overload of the motor happen? It happens when we slow the motor down in such a way that it begins to draw a lot more than what it's rated, and that's because it's not generating as much counter electromotive force. To answer these, when you first start a motor, it has high inrush current. Why? Well, now that's explained through our knowledge now of counter electromotive force. Because there's no CEMF being generated, we're going to have a high inrush of current before that counter electromotive force rises in magnitude. So that's why we have high inrush current, due to the lack of counter electromotive force. Right? Why does current drop as speed goes up? Because we're generating more counter electromotive force. This simply explains what we just went through, and it's there for you to study from. So if we apply, this is a DC motor now we're talking about, okay, not an AC motor. So if we increase the applied voltage, we wouldn't expect an increase in armature RPM, and we saw that through our labs. As we increased our voltage, our motor went faster. Right? That means also that we're generating more counter EMF. So more applied voltage, ironically, means more counter voltage that's being produced because we're spinning our armature faster. Oops, sorry. As that happens, because the counter EMF is increasing, our current draw is going to decrease. And that's why eventually we settle into around FLA if the motor's loaded. If it's not loaded, it's going to be less than FLA at rated RPM. But that's why we have less. Torque drops as current drops. So which means if I were to ask you, say, when is the most amount of torque available at a motor shaft? Well, that's right at startup. At startup, you have the maximum amount of torque available at your motor shaft because you have your motor current draw is quite high at 38.3. That's why, if you recall, when we're looking at drive parameters, we have a CL parameter, which is a current limiting parameter. And what that does is, if it's adjusted properly, is prevents excessive torque from being developed at the shaft by limiting the amount of current that we can feed to the motor. Now, it's fairly obvious, but everything's going to be opposite. If we drop the applied voltage, we would expect our RPMs to drop. Again, this is for a DC motor. If our RPMs drop, we would expect our counter electromotive force to drop because counter electromotive force and the speed of rotation are directly proportional. The faster it rotates, the more counter electromotive force. When you slow your motor down, it draws more current. Now, let's qualify that. I know in your labs that the current remained relatively constant. And that's because we had that load on the shaft, and most DC motors are known for that. But in general, if you're dropping your CMF, the DC will stay relatively constant, except when you get to low speeds, and then that's where you're really going to see a difference. But in general, on principle, this is what happens. And of course, your output torque is going to go up as you slow down. Right. Yep, just like I said. Look at that. Everything I just said, it's all online. So now let's go away now from looking at basic motor, DC motor topics, and let's look at the drives itself, specifically the drives. If you recall, when we're talking about quadrants of control, there are 4 quadrants of control, but 1, 2, and 4 quadrant controllers are the only types that exist. There's no such thing as a 3-quadrant controller. So it's important to know what they are. 1 quad controller. This is what we were just using with the, not the last lab. The lab, actually, that wasn't one quad because we couldn't reverse it. But it was the 1 quad would have been the DC drive that we were using before last, and that is we couldn't reverse it through the drive itself. We would have to unwire it, and of course, if we were to have too much counter EMF, in other words, we're feeding current back into the drive because the motor is maybe spinning faster than we're asking it to go. That drive wouldn't be able to take care of it, and you could damage the drive or blow a fuse, whatever the case may be. Our 2 quad was our AC drive. That was amongst our first labs, and that drive was able to reverse the drive all by itself, but it still couldn't take advantage of that. If there was extra counter EMF being generated, which means there's current potentially being fed back into the drive because the motor is spinning faster than we're asking it to go, or it's spinning without a speed command present, whatever the case may be. Right. The difference between the 1 and 2 quad controllers that we've personally used in the lab was that the 2 quad controller had some safeguards to that, and they would shut down, whereas the DC drive we're just using extremely inexpensive, and therefore it doesn't have the same safeguards. So it would never be used in a situation where that might actually occur in terms of excessive counter electromotive force being generated. And then lastly, you have a 4 quad controller. There's no such thing as 3, the 4. The 4 quad does everything that the 2 quad does, with the exception of that if there is excessive counter EMF being generated because the motor is spinning faster than it's being commanded, or there is no command and it's spinning and you're turning it into a pure generator, then the 4 quad controller can take advantage of that. It can regenerate that. It can take advantage of the regenerated current and power, whereas the 1 and 2 quad cannot do that. Right? So that's the main difference between the 2 and the 4 quad is that the 4 quad is regenerative, the 2 quad is non-regenerative, and by its very nature, 1 quad is non-regenerative. So again, it's not really important to know that a quadrant 1 is clockwise or counterclockwise. That's not important. What's really important is to know the difference between a 1, a 2, and a 4 quad controller. And specifically what makes the 4-quad controller different from the 2-quad controller, and that is that it's regenerative. It can take advantage of counter EMF being generated by the motor in excess of the current that it's feeding out to it. Right. So that was our 1-quad. Right. Can't reverse it. That was a 2-quad. We can reverse it. And of course, we don't have an example of a 4-quad regenerative because they're a little bit expensive. But you can refer to controllers like that. Like for instance, for this process, I need a 2-quad controller. So you could get a picture in your mind of what kind of controller you need. Okay, well, I got to be able to reverse it, but I'm not too worried about the motor getting away from me in terms of it going faster or slower. The here, if I can get to it quickly. No. Okay. The best example of that was the crane, and that was from the last lesson. A crane, if the loader is too fast, it can kind of get away from you, and it can start pulling the motor down, which means it can start to spin the shaft faster than the shaft is being commanded. So, in other words, say you're commanding the shaft to turn at 1,000 RPM, but it's actually spinning at 1,500 RPM. That means you're going to be generating more current than you're feeding into the motor. And it's going to go back into your controller. And if your controller can't handle that, then it's either going to shut down or it's going to be damaged, depending on whether it's a 1 or 2-quad controller. But if you have 4-quad, it can absolutely take advantage of that. So if you say I need a 2-quad controller, you have a picture of what the expectations and the capabilities are of your process. If you have a 4-quad controller, the same deal. There's a possibility that it can get away from you. Or when it comes, I'll get back to this. When it comes to cars, cars aren't going up and down; they're going left and right, or north, south, or east, west, depending which way you're driving. But of course, when you're driving a car, electric car specifically, of course, the tires are connected to motors, and if they're spinning either by themselves, so you're going downhill, or you're asking the car to go 50 kilometers an hour and it starts to go 60 and 70, that means that you're turning those motors into generators. In that case, you need a 4-quad controller in your car because it has to be able to take advantage of that regenerated electricity. And it can be used to either charge your batteries, or it can be fed back into the motor because it's opposite polarity. And what it'll end up doing is it'll electrically seize the motor, which is what regenerative braking is all about. So in a car, when you have regenerative braking, you can't rely solely on regenerative braking. You still have to have mechanical brake pads. But what it can do is it can significantly slow that car down before you have to engage the brake pads, which really leaves the life of your brakes a lot better, a lot longer, right? Okay, so again, regenerative braking is if it's that collapsing magnetic field you get because you're not feeding any power into it, that generates a back EMF, and that back EMF, just like if you were generating it if it's spinning too fast, can either charge batteries or be used for regenerative braking, one way or the other. So the most important thing to know about what we just discussed is that what the difference is between a 1-quad, a 2-quad, and a 4-quad controller, right? And specifically when it comes to 4-quad controller, we should be aware that it can take advantage of the excessive counter EMF that's being generated back into the drive, and that's why we call it a regenerative drive. So 1 and 2-quad are non-regenerative. 4-quad is regenerative. 1-quad is non-reversing. 2 and 4-quad are reversing. This is important. I should say also that you are sometimes asked, there's a few questions that are specific to the labs, and I might ask you in terms of what kind of controller was the DC drive we used in lab, whatever, so on and so forth. But there's only 1 or 2 like that, so you don't have to worry about it. In terms of studying hard for it, just think about what you did in the lab and just what I've just been talking about. Okay. There's nothing about diodes on the test, but this is a screen that highlights the difference between the diode and SCR. And the only difference is the SCR is a diode, but it has this gate that turns it on and off, right? So it's like the diode, it only conducts in one direction. It has to be forward biased to conduct, but we can turn it on and off by applying voltage to the gate, so we can get some fun stuff to happen with that. When it comes to the diode, if we apply voltage to the gate, and basically this is pretty pretty straightforward. As the supply AC goes positive, it'll be applied to the anode of the SCR as well as the anode of the diode. The diode, because it's going to be forward bias, will fire the gate, and the gate will conduct, and that's what we see through this the black line. And then when it goes negative, these both become reverse biased, and it prevents the current flow through the load. And there it is, pretty straightforward. What can happen with SCRs to expand on their control is that if we fire the SCRs at specific times along the input sine wave, we can actually manipulate the DC output. So this is a bridge rectifier like you've seen with 4 diodes. The only difference is we've replaced 2 of the diodes with 2 SCRs. And by manipulating the firing angle or the firing rate on those gates, we can get a very different DC output. So in that regard, we can use our SCRs for DC speed control, which is exactly what we were doing in the last 3 labs that we did. All 3 of those, all 3 of those labs and expand on the 2 drives that we used were SCR controlled. That's why it's a thyristor control. And the way we controlled the speed of the motor was if you recall, we manipulated something called the speed reference, and that speed reference essentially manipulated the firing rate on the excuse me, the firing rate on the gates. So when we are talking about the firing angle on the gates, that we call it firing angle because we'll fire it or we'll apply voltage at regular intervals along the input sine wave, and it's called an angle because the sine wave is of course angular. It goes from 0 to 180 and then through to 360. So if we can manipulate that firing angle along the positive part of the sine wave, then what we can do is this is what we'll get. We'll shave off a little bit of that output more and more. So as we increase the firing angle, we decrease the DC, the average DC. So if we decrease the firing angle back towards 0, then we increase the DC. So we have that inverse relationship between the firing angle and the amount of output we get from an SCR controlled drive. So if we quote unquote fire it at 0, you don't really fire SCR at 0. That simply means that you're leaving it on all the time. So you're never removing the voltage from the gate. Then you're going to get 100% output, right? So you get a firing angle of 0, you're going to get 100% output. If we now increase that firing angle to 90, we've decreased the output by 50% because 90 is half of 180. So as we increase it by 50%, the increase the firing angle by 50%, we decrease the output by 50%. So again, it's inversely proportional. And of course, if we increase our firing angle by 75%, which is to 135, we decrease our output to 25%, or we decrease it by 75% if you want to look at it in that frame. All right, so it's important to know that a firing angle will go from 0 to 180. The output's going to go from 0 to 100. As we increase the firing angle, we're going to decrease the output. So if I wanted 100% output, I would have a firing angle of 0. If I wanted 0% output, I would have a firing angle of 180. There's no firing angle of 180. It simply means we never put voltage on the gate. So we should know that as the firing angle goes from 0 to 180, our output will go from 100 towards 0. It's inversely proportional. This just highlights that. So if you've got a 100% output, that means your firing angle is at 0, right? If you've got 0% output, your firing angle is at 180, and that's what this is showing. So it's inversely proportional. Proportional would be this, except going from bottom left to top right. But because it's inversely proportional, it's going from top left to bottom right. So this was a sample of a question that I think I did last week or the week before. I can't remember. So we're going to expand on some of these. I've got a few questions available to you. So in this case, we've got a thyristor drive. We're putting out 180 volts DC to a motor that's rated at 180 volts. We're putting 120 volts DC to a motor that's rated at 180 volts DC, 2 horsepower, 1780. So obviously, if the motor is rated at 180, that means it's if you apply 180, you're going to get 1780 RPM. If we're applying 120, then that of course means that we're not going to be getting 1780 out of this at the moment. Right? Also, we've adjusted that max speed parameter so that it'll never spin faster than 1600 RPM. Okay, so obviously when we're doing that, we're manipulating how much voltage can be applied to the motor, or if we're going to get right down specifically about it, we're going to adjust the firing angle such that if you want your maximum speed capped to 1600, we're going to prevent that firing angle from going to zero. Because if it went to zero, then it would be full out, right? The minimum speed will allow the motor to drop to 0 RPM, which means that as we change our speed reference, we'll be able to go to 180 on our firing angle to completely take away the output percentage. Okay, current limit, we're going to do it to 90% of FLA. Fair enough. So we'd have to determine what FLA is. The motor shaft rotating at this. Now, how do we know this? Well, we know that the motor can have a maximum of 180 volts applied to it. We're applying 120. So just like a test score, this is what you can get. This is what you got. So that'll give you a percentage. Right? So 120 divided by 180 is going to give you a percentage. It's going to be a decimal. When you take the decimal and you multiply it by the 1780, 1780 is the maximum RPM, but now if we take this decimal, we multiply the 1780, that'll tell us what our speed would be if we apply 120 volts DC because it's linear. So we can rely on the fact pretty closely that if we apply 120 volts DC, using this equation, we can see that we're going to end up around 1186 RPM. Because we've manipulated the max speed setting, we can't go above 1600 RPM. So how do I know it's 18.8 degrees? Well, I do 100 minus this because what I want to do is I want to know what the percentage difference is. So 1600 divided by 1780 is going to give you a percentage, but I want to know what the percentage difference is. So if I do this, this tells me that I've got a 10% difference. So how do I get to 18? Well, 10% of 180 is 18.18. So you wouldn't multiply 180 by 10.1, you'd multiply it by 10%, which is 0.101. Okay. So again, these aren't really new equations. They're just taking existing data and applying stuff that you already know in terms of how to come up with percentages, right? So for the motor speed, according to the voltage, you just take whatever is being applied, divided by what the maximum can possibly be, times whatever the maximum speed is, and we get that from the motor rating, and that tells us what we'd be at 120. In terms of the SER firing angle, you would take your 16, we know that we're capping it to 1600 RPM. We know the maximum is 1780. So therefore, when you do this math, if you do this math and you don't minus the 100, you'll end up with 89.9. Which is not really what we're looking for. We want to know what the difference is. So what we do is we do 100 minus this. And when I say 100%, that's 1. 1 minus this, and that tells us that we get a 10% difference. Therefore, our firing angle is going to be minimal 18.8. If we go lower than 18.8, our output will increase and we'll be able to go faster than 1600 RPM. We've already discussed that the minimum speed, because it allows it to go to 0 RPM, we know that our firing angle would be allowed to go all the way to 180, because that's when we would cap our speedo, our speed commando. Right? This is not on the test. This is just me having some fun. But basically, what I do here is if you do your horsepower times 746, you end up with wattage, and if you take your wattage divided by voltage, you end up with current. This is just for fun, so I wouldn't worry about that too much, but it's just demonstrative of what you can actually do. Okay. We're coming back to some questions. I'm actually, there's nothing on the test for this. I've actually removed it because we're not able to really get into it. The only question that might be on the test about this is, why do we use MOSFETs for pulse width modulation? And the only answer I can think of is that they're extremely fast in terms of switching speed. That's the extent of your knowledge you need for MOSFETs and pulse width modulation. Why do we use MOSFETs? Because they turn on and they switch extremely fast, and we need that for pulse width modulation. Okay. Feedback devices. None of this is on the the test. This is just part of the lesson that we just did. Feedback loops. This is all from instrumentation level 1. Yeah, so none of this is really important for the test. What is important is this isn't important. Though if I say speed reference, you've used it a couple of times, but now the speed reference in the last, if you recall the last lab we did, the speed control is actually called speed reference. And in general, whether it's a DC or AC motor, speed reference refers to the speed command or the speed control. So you should just be aware of if you see the term speed reference on a test, for instance, it refers to the speed command or what you want, how fast you want something to go, and that's it. Okay. So we talked about 2 main types. We talked about a tacho generator, and we talked about encoder. The tacho generator is not on the test because I don't know. Some of you may end up with a different experience than I did, but one of my jobs was to swap out a lot of DC systems for AC systems, and the tacho generator. I haven't seen one, I kid you not, in more than 30 years. It doesn't mean they're obsolete. They're not, they're pretty, well, I guess 2-dimensional because they'll give you speed and they'll give you direction. And if that's all that's important, then that'd be great. It's probably a lot, oddly enough, it's not cheaper than an encoder, even though it's simpler technology because it's an actual motor. And because it's a motor, it requires service. So yeah, I would say 30 years ago, maybe is the last time I've ever worked with these. I'm not saying nobody's using them, but I'm going to focus on stuff that I've seen because I've traveled quite a bit. I've been overseas throughout the States. And based on my experience, the encoders and laser measurement encoders are far, far more common than anything like that. So encoders are feedback devices. They are used to measure a number of motor parameters, depending on what kind of encoder we're looking at. Right? So your encoders tend to have flex couplings because if you had a solid coupling, what happens is when you start up, you can actually end up breaking the coupling. So you have to have a bit of a flex in there so it takes up some of the starting torque if it starts full speed. Not important, just FYI. What is important is that the 2 types of encoders that are available, we should be aware of what the 2 types are and what their capabilities are. So an incremental or single track encoder will give you just speed and distance. Right? It will not give you direction because it's a single track. So as the LED shines through the gaps, the rate of flash, if you will, on the photosensor will tell you how much distance is traveled because you know how many slots are on a disk. It'll all tell you how much speed there is because of the rate of flash will tell you how much speed there is, of course. Right? So this is great if, for instance, you are going in you expect your process to only ever go in one direction. You don't care if you have to reverse it. It's the simplest of them all. And it's just by looking at you actually can't tell whether it's an incremental or quadrilateral or 2-track because they both kind of look the same. You'd have to look on the label to see whether it's incremental. It'll have more, the dual track will have more, but you can't really just look at it and see it. You have to read the label. The one sort of beyond that is a 2-track. The 2-track, which is also called a quadrature. The 2-track will give you speed, distance, and shaft direction because of the offset. You'll either have an offset set of discs, or the discs will have 2 sets of slots on it that are slightly offset. 6.5 does the other. It's going to end up doing the same thing. A will flash before B, or B will flash before A, and you can tell which one flashes first, which that'll determine what direction you're going. This also tends to be a lot more accurate than the 1-track because you have a little more finer resolution on the slots. So 1-track, incremental or single track will give you speed and distance. The 2-track will give you speed, distance, and shaft direction. We looked at this and I said minimally the incremental or the single track encoder would be fine for this. But I said if I were making recommendations to a client, I would probably go with the 2-track or a quadrature, only because if there's a possibility of there maybe being a screw up at the cutter and you have to reverse this, you might want to know how much you reverse it, because that will through your controller might be translated into how much material you reversed, so you'll know how much run out you're going. This is not on the test. This is just FYI. Right? But minimally, 2-track. Right? This isn't on the test, but there certainly will be questions about the incremental control and a 2-track incremental controller. Okay. I promised I'd get to the questions. This is the one that we just did. Okay. The only thing that you're not going to have to worry about is this. But now let's look at something else. Here's some more parameters. I've got a motor parameter. This is the motor parameter. The motor is rated for 180 volts DC, 750 RPM, 3 horsepower, 15 amp. Okay. The max speed of parameter has been adjusted to 1650, which is below what the maximum rating nameplate is. And the minimum speed is not going to be 0 this time, it's going to be 50. So we don't want it to go to 0 when we turn the minimum speed down. Just to sort of define that, minimum speed doesn't mean it will never go to 0. Minimum speed is how slow it will go while it's running. But if you push stop, it's going to stop. It's going to go to 0. This just means that as long as there is a speed command present and that we're telling the motor to go, if we turn that potentiometer or whatever it may be down to 0, the motor itself will never go to 0. It'll stay at 50 RPM for a number of reasons. Tug of war is a good example, but anyway. So we know that the motor can handle a maximum of 180. We're going to apply 110 volts. Okay. If we apply 110 volts, what's that give us? That gives us now where do I get this 110 for? This is just me throwing numbers out there. This is indicative of what you'd see on the test. You'd get these parameters and say, for instance, what would the shaft speed be at if we applied 110 volts? And this is what you do. You'd have to know what your maximum voltage is. You'd have to know what your maximum RPM is. And then, of course, you'd have to be given what this is. And then when you're given that, you simply divide the voltage given by the maximum voltage and you multiply that by the maximum RPM, and you'll end up with an RPM, a given RPM. Because the max speed is 1650, remember it says below, so the closer we go to 0, the more RPM we're going to get. Therefore, now that one, I'm going to explain this in a second, because just like that when I showed you before, it said 100% minus this is the same thing, but this is just more what you would put into your calculator. So if you want to know what the firing angle would be at 1650, well, you'd know that if you had a firing angle of 0, you'd have 1750, because that's your maximum speed. And you know that your span for your firing angle is 180. So what you do is you see what the 1650 is over 1750, which is a percentage, but you do them 1 minus because you want to know what the difference is between the two of them, right? So the difference between the two of them, whatever that may be, you multiply that by 180, and that tells you that in order for the max, because the max speed is adjusted to 1650, no matter how far you crank up your speed reference, it will never fall below 10.28 degrees unless you stop it. Right? Now we have a minimum speed of 50. So the maximum firing, remember, as we go towards 180 degrees firing angle, our output goes down. So that's really where the end at which we're adjusting minimum speed. It's the same equation, exactly the same. Of course, though, we'd have a lot larger number because we know that as our firing angle increases, our output decreases. Right. So exact same equation, and it's not really a new equation. This is just a percentage. But again, you would have to be given things like you'd have to be given all of this, but what you wouldn't have to be given is 180, because that's what the firing angle maximum from 0 to 180. Again, the current limit, that's just there for fun. That's not on the test. Don't worry about it. Here's another one. 90 volts, 1750, 1 horsepower, 10 amp. We've adjusted the max speed parameter so that it will never go faster than 1580. We have the minimum speed, so it never goes slower than 15 RPM. This is just easy for fun, this one. So we got 80 divided by 90 times 750. That's 15. Does that make sense? Well, yeah, of course it makes sense, right? Max speed, this is where SCR. That's going to be the same equation again, right? Same equation again. And of course, don't worry about this. Okay. So why I'm going through this, and I'm going pretty fast, but there are a couple of questions like this on the test. So all you need to do is refer to these slides, study these slides, and you can you'll be in good shape. Don't worry about the current limit and figuring out what in terms of horsepower. That's not on the test. What is on the test are these sorts of things. Okay. So for instance, if these are the only questions I've given you, how do you study? Well, one way to do it is if you've got this, you've got two motors that I've given you. If I've given you this one and I've given you this one. Okay. What you can do is you don't have to worry about the horsepower on a 15 amp, but simply apply different voltages to it. So if you want to see if you're on the right track, apply 90 volts to this, and what you should get is half of 1750. So what I would do is I would use the exact same parameters, and what I would do is I would change the applied voltage to see what you get. Now, when I say apply, you should work in groups to do this. Right? The same thing with this. Change your maximum speed settings and see what you're firing as. That's the best way to study and practice for this. I would do the same thing with this, right? Exact same thing. I wouldn't worry about that too much. So I'm kind of assigning homework, I suppose, in regards to that. And what that is if you are doing that, what I asked you, you can even use this one if you want, but this is the same motor. If you're doing that, as you're going through it, and you're having issues with it, then that's when you email me, and that's maybe what I can address on Monday, because I think I'm going to just do the test on Tuesday. I can address that on Monday. So even tomorrow, I'm still there. If you're working through these things and you want some clarification, you're on campus anyway. You know I'm going to be there early. Come on down and have a jibber jabber if you like. Okay, but that's the way I would do that if for this, other than studying for the other stuff, is that just use the motor I'm giving you, but just change these settings here. You know, the 1650, the 50, the 110, whatever. Just do that, and then see how you feel about the math. Do it in groups, which is, if you can, which is always better. And then you can come see me tomorrow, or you can email me anytime. And of course, I can address anything next Monday as well. So same deal, right? You've got a 180 volt, 1790 RPM DC motor. What's your expected shaft RPM with a firing SCR firing of 90 degrees? Well, this one's easy because all you have to do is take half of 1790 RPM. Because what do we know about 90-degree firing angle? We know that that's 50% of the range, and we know that the firing angle and the speed are inversely proportional. So 50% of that is going to be exactly what you would expect. So 895 is going to be half of 1790. Now, same deal. You've got 180 volt, 1790. What's your expected voltage output with an SCR firing of 90 degrees? Well, it's going to be the same thing. We know that 90 is whatever it is. 180 is the maximum firing angle. We want to know what the difference is. Now, this one's easy because it's going to be 0.5 no matter what. But now, instead of the RPM, you multiply the voltage, because what do we know about firing angle and voltage? Just like speed, it's inversely proportional. It's going to be pretty easy. So that same equation that we looked at in the last 2 or 3 slides. See, when adjusting the maximum speed parameter of a thyristor thyristor is just an SCR DC drive to limit shaft RPM, we are preventing the firing angle from, this would be multiple choice, reaching 0 degrees, right? In other words, if we go to 0, it's going to go full speed. If we don't want it to go full speed, then we want to prevent the firing angle from getting to 0 degrees. And of course, the opposite is true when we're adjusting the minimum speed. We want to prevent it from reaching 180 if we don't want it to go to 0, if we want to keep it above 0 RPM. That, my friends, is that. Easy, easy peasy. All right. I'm going to hang around if anybody wants to talk, if work through things. But what I would encourage you to do is, like I said, on those last few, just take the motors that I have, just apply different voltages to them. 30 volts, 50 volts, I don't know, don't play 190 because that doesn't make any sense. But same with your RPMs, just choose something that's less than 1750 and see what happens in terms of this. Yeah, I mean, that's it. Pretty easy, right? Same deal here, right? Use that motor, apply different voltages and RPMs. There it is. Even this one. If you want for this, just change the firing angle and plug it into here, and then take a look at it. It's pretty straightforward. So in terms of studying, well, what are the important things on this test? You should certainly be aware of what a commutator is all about, and what the commutator and what the brushes are all about. The brushes apply the voltage to the commutator. What does a commutator do? You should be aware of that. You should be aware of the different types of shunt motor and what their capabilities are. So different types of DC motor, excuse me, the shunt motor, the DC motor, DC series motor, what its capabilities are, and what thing you should look out for, as well as a compound motor, not only its capabilities, but what happens if we reverse them. So in regards to this, I should be aware of what is the one common method that you can reverse a DC motor, and that's of course to swap the armature leads. You should be aware of counter electromotive force and how that increases with speed, and how the relations between voltage, RPM, CMF, and current and torque, what those relationships are, and why is there high rush inrush current? It's right there. I don't know how else to broadcast it even more. And then you should be aware of what a 1, 2, and 4 quadrant controller capabilities are, what the main differences are. Have a passing knowledge of what regeneration means. It means that it can take advantage of extra counter electromotive force being generated by the motor if the motor is going faster than the speed command, or if the motor is spinning by itself, and in which case it becomes a generator. Uh, you should be aware of the SCR in terms of anode, cathode, and gate, and how the SCR behaves in terms of it being forward bias and voltage on the gate. You don't have to be aware specifically of that, but you should be aware of firing angle, how as firing angle increases, DC output decreases. Right? Uh, uh, I've just made a decision, and that is I'm removing the MOSFETs from the test. MOSFETs, that it's gone. Don't even study it. That would have been more appropriate in AC. When it comes to these things, this is just FYI. But in terms of studying, you should be aware of what a speed reference actually is. It's a speed command, right? There's also current reference, but more often than not, you're using a speed reference, and that simply means that your speed command out to something. There is a tachometer on the review. It is it is not going to be part of your test. What will be part of your test in terms of feedback devices is the two types of encoders, both the incremental single track and the 2-track. They're both incremental, of course. This is also called a quadrature. Honestly, I rarely referred to it as that. When it comes to quad controllers, you're generally talking about drives when it's a 4-quad controller, 1 quad, 2 quad, 4 quad. So 1-track and 2-track are the two main types. 1-track can give you speed and distance, of course, speed, distance, and shaft. For the 2-track, be aware of that. Don't worry about that. And of course, there's questions based on firing angles and what we know about firing angles and speed and voltage and those relationships. That's it. That's all I've got. So again, I would encourage you to take the motors I have here, plug in different numbers, and use those equations. If you want to come see me tomorrow just to go over some of this stuff, that's what they pay me for. I'll be there. I'll be there early. You can do it during the week and email me. You can wait till next Monday if you want to go over some things with me. There it is. So again, just to reiterate about what's happening tomorrow, you do not have to come unless you want to make up a lab. And even then you don't have to come. In general, you don't have to come. But if you want to make up a lab, then you show up tomorrow. If you want to just redo one of the labs, or you're curious about stuff, come on over. The equipment's there for you. Or if you want to just talk to me, here I am. I'll be there tomorrow. Okay. Next week on Monday, I have nothing planned for Monday other than me hanging around online and answering any questions you might have. And then we'll do the test on Tuesday. I think that's probably a better idea. Okay. So like I said, I'll be around for a while. I'm not going anywhere. How much time do I got here? Let's say another 15. And then I'll see you whenever. All right. Yeah, what's happening? In the AC lab, yeah. Well, were you able to reverse the motor in the DC labs? Did you push a button and the motor went the opposite direction? Yeah, so it's a one quad controller. Yeah.